Okay, let's talk a little bit about column store indexes then, a particular type of index that I can use to work with my data. And in this case, we're back to our sales.product table. You can see I've got my product ID, my name, my price, and my supplier in that table. And I want to be able to query that, and I want to do it using really high performance. Perhaps this table is part of a data warehouse. So maybe this would be perhaps a dimension table that I would have in a data warehouse, and I'd have a fact table that had maybe the sales of the products or something like that. And what I want to do is I want to take my index, and rather than have my index organized like this in these sort of pages that contain rows, which is a traditional index would store it, I want to store it a slightly different way. I actually want to split those into row groups and index the columns. I actually want to be able to use the columns as the basis of the index. So we've got row groups that are then organized into these segments that are going to be the columns that allow me to store the indexes. And that's going to allow me to take advantage of things like compression, because a lot of these columns may have multiple rows that have the same value, and that makes them nice and easy to compress, and then we can store that in memory, and that's going to optimize my ability to query that. So we compress these segments, we put them in memory, and we're then able to query them using this column store idea. So it's a slightly different way of thinking about indexes. And what we're going to do is we're going to create this using a similar syntax to what we saw before, but this time it's create clustered column store index, and then the name of the index on the table. Now you'll notice, because I'm creating a clustered column store index on a table, I haven't specified any individual columns, because I can create a column store index for the entire table. And it's just going to create an index that has all of those different columns, those segments stored in memory, and I can then query that using the column store index and get the benefits of performance. So that's a clustered column store index. I've also got the option of creating non-clustered column store indexes. So I can create a non-clustered column store index, and then I can specify the individual field names that I want to use in this case. So I've created that on the product ID and the name. Those might be the ones that I most commonly query, so I can go ahead and create that column store index on those. So column store indexes then, the important things to remember from the point of view of really just getting the fundamentals of this, they are stored in memory, and they store the data by column instead of by row. So traditional indexes, you're really indexing to find a row of data. Here we're indexing by column, and that allows us, when we've got columns that have multiple instances of the same value in that column, we get really good compression ratios that allows us to compress that data, compress the indexes, and store that in memory to improve performance. They can be clustered or non-clustered, and a clustered column store index can include all of the columns. I can just create a clustered column store index on the table, and that will by default include all of the columns in the table. And I can create only one clustered column store index per table. That's important to remember as well. When you create a table, just like an ordinary index, you can only have one clustered index. You can only have one clustered column store index per table.
Wow, column store indexes look kind of cool. Can we see some more?
Sure, let's have a look. Right, well, we're going to take a look at column store indexes. So again, I've got a couple of tables here. I've got one called dbo.product and one called dbo.product inventory. So I've got a table of products, and then the inventory table tells me information about how many of those products I have in stock and where they're stored in the warehouse. So if I have a look down here, I can see here's the product table. I've got a list of products with their names and numbers and all that sort of thing. And if I scroll down underneath that, I've got another table called product inventory, where I've got the product ID, so that's what we're relating the tables on, and then I've got various locations, shelves, bins, and quantities of where I'm storing that product in my warehouse. So again, we're going to turn our statistics IO on like we did in the previous demo, where we looked at just regular indexes, because I want to see what's happening when I go and query these two tables. And I'm going to stick on the actual execution plan here, just so we see what's happening under the covers. And we're ready to go and query these tables. Now this query, we haven't really looked at the syntax in any detail before, but we're selecting the name of the product from the product table and the list price, so the product name and the product list price. And then from the inventory table, we're bringing back the shelf, the bin, and the quantity. And we're bringing that from the product table, which we're just calling P, just for convenience, and joining that to the product inventory table, which we're calling I, and the join is based on that common key. Remember that foreign key relationship we talked about way back at the beginning, where we've got our product ID that relates to the product ID in the inventory table. And then we're filtering on the product name. So it's a bit more of a complicated query than we might have seen so far, But fundamentally, we're just bringing back some data from both of these tables, and we're filtering based on the product name rear brakes. I'm only interested in that particular product, and what I want to know is bring back the name and the price of that product and the shelf, bin, and quantity that I have in the warehouse. Let's go ahead and run that query. And I get it back, and I can see, well, I've got 3 rows, so there's 3 locations where I store that product on shelf E, shelf M, and shelf W, and I can see the bin and the quantity that I have in the warehouse there. So let's have a look at what happened when we ran that query. If I look at the execution plan, it basically did 2 table scans. Because these tables are heaps, there are no indexes on them. So we've scanned the products table, we've scanned the product inventory table, we've used a hash match to join those things together. Don't worry too much about the details of that, but we've joined them together and got back the results. And if I look at the messages, I can see for all of the different operations that happened there, the number of reads that happened. And I'm interested in the logical reads. So I've got my product was logical read 13, and my product inventory table, there were 7 logical reads that returned that data. So a fair amount of work going on under the covers to return the information. Let's create a column store index. I'm going to create a clustered column store index. And a clustered column store index is always based on all of the columns in the table. So we're going to create that on the product inventory table. So clustered column store index. And now let's go and run that same query again. So here we are. We're going to bring back all of the locations in my warehouse for my rear brakes. And we get back the same results. And this time, if I look at the execution plan, we've actually, when it came to taking the data from the products table, we still don't have any indexes on the products table, so we just scanned that table. And that was 71% of the cost of the query. So 71% effectively of the effort was involved in scanning that table. And then we've used this column store index that we created on our product inventory table to bring back the data from that table. And if I look at the messages tab here, well, there are fewer operations. There's only 3 operations going on here. And what we've done here is we've still got logical reads going on from my product inventory table. There are actually none because it didn't need to get them. It got them from the from the product inventory table. There are no logical reads. It got some logical reads from the product table, but it read a segment from the product inventory table. So when we have a column store index, we're actually storing the data column-wise in segments. So it only read 1 segment from there, and it was able to get that data. Well, let's see if we can further optimize this by adding another column store index. This time we'll add a non-clustered column store index on the product table. And because it's a non-clustered index, we can specify individual columns. So we're going to have a product ID, name, and list price columns in this index. Let's go ahead and create that. And again, we'll go and run that same query again just to see what actually happens under the covers. Get back the same results as you would expect. And the execution plan this time, it uses both of my column store indexes. It uses the clustered column store index on the product inventory table, and it uses the non-clustered column store index on the product table to bring back the data. And again, when I look at the operations here, I'm getting segment counts here because it's reading those segments from the in-memory column store index, and that's going to optimize the query and make that perform faster. We don't really notice it, particularly in this example because it's such a small table, but with a very large table that you might have in something like a data warehouse where you've got potentially millions of rows, then this type of operation can really improve the performance of your queries.